Welcome to part 4 of two-dimensional autonomous systems. So we are considering this system in which the state variable has entries x1 and x2. These are functions of time. So really we have x as a function of time, x of t, and this means that we have x1 of t, x2 of t, x1 at time t and x2 at time t. So A is a matrix with entries defined here, and this is a way of writing two equations. The first equation will be A11 x1 plus A12 x2. The second equation will be given by A21 x1 plus A22 x2. Okay, so I'm almost running out of space here to write both of those equations. And this side here, which in short we would write matrix A is a 2 by 2 matrix, matrix A times column vector X, that's the right side of the differential equation. This is a function of X, and therefore the motivation for calling this, actually you could argue that this is of the form t comma x, even though explicitly the independent variable t does not appear here, but that's also customary. But this is the motivation for calling this an autonomous system. The dimension of this system is dimension 2. And now we had, quite a while ago, we had referred to an operator called determinant. Okay, determinant of a matrix in this case is going to be in reference to determinant of this matrix A. Well, now we have another operator called trace. The trace of a matrix, which we're going to define in just a minute. Okay, this will be another operator defined on the matrix of coefficients here with entries A11, A12, A21, and A22. And we would like to consider a plane, just, a plane has two axes. The horizontal axis is going to be the trace, and the vertical axis is going to be the determinant of this matrix. So there's something, there's some information that we would like to summarize in this plane, and this is the subject that we discuss now. Next, we compute the eigenvalues of the matrix A. We compute this characteristic polynomial, and we use the variable or expression lambda. We're going to compute a polynomial in lambda, and we can see that one of the coefficients here is denoted with the letter t. So t is going to denote the trace of the matrix, and d is going to denote the determinant. So let's talk about the trace. The trace as an operator is simply the addition. Whatever the entries in the diagonal, whatever they are, we're going to add them together. Okay, this is a much general definition. As an operator, you can define the trace of any matrix with n rows and n columns, but in particular we're working with matrices that have 2 rows and 2 columns here. So if we add the entries on the diagonal, that quantity has a name, and that name is the trace of that matrix. D is an operator that we know from before. It's called the determinant, and is defined in a very specific way. You use the diagonal entries to multiply each other, and then you multiply the entries that are off the diagonal and subtract the latter from the product of diagonal entries, right? It's a very specific way of defining the so-called determinant of the matrix. Very importantly is that we have managed to write the characteristic polynomial, the polynomial we use to find eigenvalues, right? So eigenvalues are roots of this characteristic polynomial are the so-called eigenvalues. Okay, so we have expressed this polynomial with coefficients 1 minus t and d. So remember, the classical way of calling these coefficients would be something like a, we would write something like a lambda squared plus b lambda plus c. So these coefficients now, a is 1, b is negative t, negative the trace, and c would be the determinant. And this thing about finding roots of a quadratic, well, those roots are given by the formula that we call the quadratic formula, which is something that looks like minus b plus minus square root of something divided by 2a, and this argument of the square root is going to involve the classical sense b squared minus 4ac. Well, now coefficients are a equals 1, b is minus t, and c is what we call the determinant. So we obtain two roots. They are going to be distinct or not equal to each other, provided that t squared minus 4d is different from 0. So if t squared minus 4d is different from 0, then so we can say if this, then we have distinct eigenvalues. Okay, and so importantly, this scenario of distinct eigenvalues is relevant because that's precisely the scenario where we can use the eigenvalue method. Okay. Well, so let's now consider there is actually something that relates the product of eigenvalues. Well, let's just see it. So if we compute the multiplication or product of eigenvalues, okay, lambda 1 times lambda 2 by using the expressions in the roots of the quadratic equation that we just discussed, then we're considering this product. And this product looks very much to be a product of this type, a plus b multiplying quantity a minus b. You could multiply this out, distribute a times a and so on, but you may remember that this reduces to a squared minus b squared. Okay, so in this case, a is the trace, so here you want to see the trace as the quantity a, and the quantity b is this square root. So if we do that, and then the denominators, when they multiply each other, they become 4. So if we do that, then we obtain this expression, and you can see that this minus is going to affect t squared and is going to affect minus 4d. In particular, the t squares are going to cancel, and we end up with 4d divided by 4, which is d. This is d, meaning the determinant of the matrix is always equal to the product of the eigenvalues. This is something very useful because it allows you to know what the product of the eigenvalues is without even computing the eigenvalues. Okay, if I remind you, d is the determinant of a, right? So determinant, when we say d, we mean d equals determinant of the matrix A. The eigenvalues of this matrix A, they are quite a different thing, right? They are the roots of this quadratic, but without even knowing what they are, we can know what their product is. That's what's important about that result. Another thing to note here is that determinant of the matrix A is not the same as this determinant of this matrix. This matrix here, where we're subtracting lambda, that's the matrix using the definition of characteristic polynomial. They're similar, but they're not quite the same matrix, right? So when we refer here to the letter D, capital D, we're referring to the determinant of the original matrix. And now we're going to talk about a similar powerful result in which we can compute an expression for the addition or sum of eigenvalues. We're simply adding the quantities that we had computed from the formula of roots of a quadratic equation, right? And we can see that easily this square root cancels. When you're adding, it's going to cancel with this other square root, and you're left with 2 times t over 2, which is exactly equal to the trace. So even without computing the eigenvalues, this result tells us that the addition of the eigenvalues is always equal to the trace, which in this case is the addition of the entries A11 and A22, right? So even though these are the entries on the original matrix A, adding those entries, the trace, is exactly equal to the addition of the eigenvalues.